Hi, my name is Ben Owens, and in this video we're going to continue our discussion on sampling distributions. A sampling distribution considers some statistical measure, which is usually the sample average, and lists the probabilities for all possible values considering all possible samples of a certain size from the population. Let's look at a small example of this. Suppose you have a population that consists of just 6 people, and you want to consider all the possible samples of 2. Well, how many 2-person samples are there? Well, since we have 6 people to choose from, and we're choosing 2 of them without replacement, and the order doesn't matter, the answer is 6 choose 2, or 15. Here would be an example of such population. We have 6 different people, and we're going to look at all the possible samples of 2 that we can pull from that population. Taking all the possible sample averages and putting them into a probability distribution gives us what we call a sampling distribution. Although this past example is useful for developing a basic understanding of sampling distributions, it's not very realistic. Typically, we're going to be dealing with much larger populations and much larger samples. In this video, we're going to be considering certain sampling distributions involving these larger populations and samples. Now imagine this situation. Suppose you were to consider a sampling distributions for students at NCTC. The student population at NCTC is around 10,000, so if you wanted to consider every possible sample of size 30, how many samples would there be? Now, we treat this the same as we did before. Since we have a population of 10,000 and we're going to be taking samples of size 30, the total number of possible samples is 10,000 choose 30. But that number, as you can see, is 3.6 times 10 to the 87. Now what this means is this is an 88-digit number, which is huge. So dealing with sampling distributions in the same way that we did with the small population is not very feasible. Clearly, working with such a large number of possible samples is unreasonable, but luckily we don't have to. Instead, we can simply use the normal distribution because of what we call the central limit theorem. In this video, we will discuss why and when the normal distribution is appropriate and how to use it to answer probability questions dealing with sampling distributions. Let's think about this question from probability. Suppose you own an electronics store and you receive a shipment of 50 cell phones containing 7 of which are defective. If you were to choose a sample of 5, what is the probability that all of them will work? Well, it turns out there's lots of different methods for solving this problem. The first method is kind of like a sock drawer problem, and it's one where you can simply use the multiplication rule of probability. If we want to know the probability that all of these selection of 5 are good, then we simply have to find the probability of each draw being good. So if we have 43 good cell phones and 7 bad ones, and we want to pull out a sample of 5, then the probability that the first cell phone that we draw is one of the good ones is simply 43 divided by 50. So that's our probability that the first draw is good. And then the probability that the second draw is good, given that the first one's good, is 42 over 49. The probability that the third draw is good is 41 over 48, and so on and so forth. Multiplying these all together gives us the probability that our sample of 5 will contain all good cell phones. A different method for solving this same problem involves using combinations. If we wanted to find the probability of getting a sample of 5 that are all good, We could do that by thinking about how many possible samples could we make that are all good. That is, if we take the number of all good samples divided by the total number of possible samples, that will give us the probability of getting that all good sample. So the way we do that is we use combinations. If there are 43 good items, then there are 43 choose 5 ways of drawing a sample of all good items. And if we divide that by the total possible number of samples, which is 50 choose 5, that will give us the probability of getting a sample that's all good, which was 0.4543, exactly what we saw before. Now, if we tweak this problem just a little bit, so in this case it says, suppose you own an electronics store with a shipment of 50 cell phones, 7 of them are defective, and you want to take a sample of 5, but what is the probability of getting exactly 2 of them that are defective? Now in this case, what that kind of means is that, okay, if exactly 2 are going to be defective, then that means we want 2 that are defective and 3 that are good. The way that we solve this is we have to use these combinations. So if we wanted to split up our sample, we want 3 good ones and 2 bad ones. And so the probability of getting those 3 good and 2 bad is simply 43 choose 3, so that is the number of good ones, choose the number of good ones we want, times 7 choose 2, which is the total number of bad ones, choose the number of bad ones that we want, divided by 50 choose 5. This will give us the probability that our sample of 5 will have exactly 3 good ones and 2 bad ones. Now, if we make a distribution of all the possible numbers of good and bad, this is what we call a hypergeometric distribution. For this situation, here it is. Notice that, getting a sample that contains 0 good ones, although it's possible, is very unlikely. And the likelihood goes up as the number of good ones increases. This is an example of what we would call a sampling distribution for this situation. So what does this have to do with sampling? Whenever a population is split into 2 separate groups and a sample is taken where the number of people from each group is noted, that sampling distribution is hypergeometric. In other words, the way that we solve it is much like the way we looked at this last example. There's lots of things that involve splitting the population into 2 groups. Anytime you have a yes-no type question, that's going to split people into 2 groups. Anytime you're trying to compare the males and females, that's going to split people into 2 groups. Anytime that the population is simply divided into 2 groups, that is going to use the hypergeometric distribution as our sampling distribution. So here's a good example. During an election season, opinion polls are vital for candidates to determine if they will win or lose the election. It helps them to know whether they ought to spend more time and money on their campaign. Suppose that Denton, Texas has 80,000 eligible voters, and 41,000 of them support candidate A, and 39,000 of them support candidate B. Let's explore the sampling distribution for a sample of 100 people taken from that population. We can think about this situation using what we call a box model. In other words, we know that our population is 80,000. We know that for candidate A there were 41,000 and candidate B there were 39,000. And we know that we're going to have a sample of 100. Imagining them as simply individuals in this box, it's kind of like a big sock drawer, a really big sock drawer, considering there's 80,000 people. But answering this question is simply finding the hypergeometric distribution for this situation. If we look at that hypergeometric distribution, this is what we see. Now notice that, of course, we need to consider all possible, ways of getting the sample, which are 0 through 100. Of course, doing this in Excel, it's pretty easy. And here we would have it. This would be the distribution, the sampling distribution for this situation. Now, of course, seeing a big list of numbers isn't that to me, it's not really that useful. I like to actually look at a graph of this, and so if we made a probability histogram of this same thing, here is what we would see. So this is the hypergeometric distribution histogram for this situation. Now, as you can see from this example, the sampling distribution looks very much like a normal distribution, and this is no coincidence. Under certain conditions, the sampling distribution will be approximately normal, and therefore we can use the normal distribution to answer certain questions. We'll be exploring these conditions later in the video. Let's look at a different example. Texas Woman's University has 9,515 students. Now, 8,458 of them are female, and 1,057 of them are male. If a sample of 30 students is taken, what is the probability that the sample will contain more than 25 females? We're actually going to look at 3 different ways of answering this question. The first method, and I think the most appropriate method, is using the hypergeometric distribution. We want to find the probability of having more than 25 females, and so we think about this as a box model where we're drawing from this box without replacement. So it's basically like a sock drawer. If we were to look at our hypergeometric distribution for this situation, here we have it. And so if we wanted to find the probability that x is greater than 25, all we need to do is add up all the numbers that are greater than 25. That will give us our probability, which is 0.7645. This, to me, is the most appropriate answer to this question. However, we could also use the binomial distribution. Now, the binomial distribution, if we wanted to use it to answer this question, is going to be as if we were drawing from this box with replacement. In other words, once we select a single person, then we throw them back in, and we have the possibility of maybe choosing them again. And so we think about this as drawing with replacement. Now, of course, when we're using the binomial, we need n and p, and so in this case, n, of course, is 30, the size of the sample, and p is simply the probability of being a female, which was, around 88, 89%. If we look at the binomial distribution for this situation, here it is. And so finding the answer to this question, the probability of x being greater than 25, is once again simply a matter of adding up these values, and we get 0.76429. Now, as you can see from this chart, and as you could see kind of from the answers that we got in the last problem, the hypergeometric and the binomial distribution are very close, at least in this situation. Technically, when you choose a sample from a population, that selection is done without replacement. So the hypergeometric is more appropriate. But the binomial, in many cases, is so close to the hypergeometric that you can use that if you'd like. And in practice, the binomial distribution is a little bit easier to use. And so many people simply use that instead of the hypergeometric distribution. So you might wonder, so why is it easier to use? In the binomial distribution, there's only 2 parameters, n and p. And those numbers are usually pretty easy to find. I mean, clearly the size of your sample and the percentage of the population that has a certain quality. That usually is fairly easy to find. The hypergeometric needs 3 parameters, and although these are, I guess, equivalently easy to find, these numbers, n and g, oftentimes can be much bigger, like very large numbers. And so sometimes it's a lot harder to use those, and so a lot of times people will just use the binomial distribution. But wait, there's more. You can also use the normal distribution to answer the same problem. We have seen that in a lot of cases, the binomial distribution looks a lot like the normal distribution. And so we can actually use it here. And so we'll look at this example of how to use the normal distribution to solve the same problem. To use the normal distribution, we need 2 quantities, and that is the average and the standard deviation. The average and standard deviation that we want to use in this case are going to be the expected value and the standard deviation for the hypergeometric or the binomial distribution. Now, you might wonder, well, which one should we use? Should we use, this, or should we use this? Well, it turns out that these are actually more or less the same. Notice that if you take the number of good items in your sample divided by the total population, that is simply going to be the proportion of good, which is the same as P, the probability of being good. And so these two numbers are actually the same. The same number here and here, all these are the same value. Also, if you think about the number of bad in the population divided by the total, that's just the proportion of bad, which is just 1 minus P. So as you can see, this average and standard deviation are pretty much the same except for this last quantity here, and that's what we call the correction factor. Now, if you remember from the last video, the correction factor is pretty much equal to 1 or very close as long as the size of the sample is small relative to the population. And so these two values, the expected value and standard deviation for these two distributions, as long as the sample is small compared to the population, will be more or less the same. So when we use the normal approximation for these kinds of things, we just use those values that we would get with the binomial. So let's look at using the normal distribution to solve the same problem. If we use the expected value and standard deviation, we get that expected value is 26.67, the standard deviation is 1.72, and so therefore, finding the area to the right of 25, we use the z-score. We get the probability that z is greater than negative 0.268, which is 0.7517. Now, one thing that I should note here is that we did use 25.5 in our computation here instead of using 25. This is because we're using a thing that we call the continuity correction. And so it makes for a more accurate prediction. Now, looking at the three answers that we got for these three different methods, you can see that they're all very close. In fact, the hypergeometric and the binomial are super close, and then the normal distribution is not too shabby either. It's a little bit off, but not too bad. So as we can see, each of these methods, it would be a good method to use for solving a problem like this. Now, looking at the hypergeometric and the binomial distributions side by side, we can see that in this situation, they really do coincide almost exactly. I mean, there's a slight difference in them, but it's very, very small. If we look at the normal distribution as well, we can see that it is a little bit different than the other two, but it still follows along pretty well. I think the biggest difference maybe is simply the fact that the normal distribution sort of continues on past 30, whereas the binomial and the hypergeometric stop, but it still is a pretty good approximation. So when is it appropriate to use the normal distribution for sampling distributions? In order to use the normal distributions, we need for two things to occur. First, the sample size must be small compared to the size of the population. This guarantees that the hypergeometric distribution will be close to the binomial distribution, or that the correction factor will be close to 1. The second thing we need is that the sample size is big enough for the hypergeometric or binomial distribution to look normal. This is going to be affected by a few things. Of course, the size of the sample is going to make a big difference, but also the proportion, that is how close to 50-50, say the good and the bad are, or the different things that we're measuring are. So these two things are actually going to sort of matter when it's seeing whether things are normally distributed. Now, there are many methods for determining whether a distribution is approximately normal, but for our purposes, we're going to use the following formula. We're simply going to take the size of the sample times p times 1 minus p, and if that is greater than or equal to 10, then that tells us that the sampling distribution should be approximately normally distributed. That is, it's pretty close to a bell shape, and so we can use the normal distribution. Now what we want to do is look at some binomial distributions and just see if this is the case. Here we have 10, and we want to see if we have a sample of size 10, how the binomial distributions look for different values of p. Now here would be if p is equal to 0.01. Now this would be an example where you have 1% of your population that believes something and 99% that believes something else. And so this would be a very skewed distribution, as you can see. If we look at p is equal to 0.1, you can see that it's a little bit more curved, but it's still very much skewed. As we get closer to 0.5, things start to look more normal. And at 0.5, things really do look pretty normally distributed. Of course, moving away from 0.5, if p is 0.7 or 0.9, it once again starts to look skewed, just in the other direction. And if we look at, say, 0.99, it's very skewed. Let's look and see what happens if we have samples of size 50. Now, we're also going to include this quick check to see if these things are greater than or equal to 10. Here, if we let p be equal to 0.01, then our computation is 50 times 0.01 times 0.99, and that's equal to 0.495, which is certainly not greater than or equal to 10. Of course, as we can see, this is definitely not a normal looking distribution. So we shouldn't use the normal distribution here. What about if p is equal to 0.1? Now in this case, we do kind of have a slightly bell shape, but maybe it's still a little bit skewed. Let's see what our quick check says. If we multiply 50 times 0.1 times 0.9, that's equal to 4.5, which is still not greater than or equal to 10. So I would probably recommend not using the normal distribution in this case. Now what if p is equal to 0.3? Here we see that it is a much sort of more even bell-shaped. It kind of trails off on either end. If we were to put it to the formula, 50 times 0.3 times 0.7 is 10.5, which is greater than or equal to 10, which says that we should be okay to use the normal distribution. And then finally, if p is equal to 0.5, we see that it's, when we compute this, it's greater than or equal to 10, so we can definitely use the normal distribution here. Of course, continuing on, if we take 0.7, that is going to also give us 10.5, so we can use the normal distribution. But if we were to look at 0.9, it's just a little bit too skewed. It doesn't fit our quick check, and so we can't use the normal distribution. And of course, 0.99 is not even close. Let's see what happens with a sample of size 100. If p is equal to 0.01, once again, it's not even close, and so clearly we should not use the normal distribution here. If p is equal to 0.1, now this is starting to look fairly normal, but it's a little bit skewed. It's not exactly symmetric. And in this case, notice that when we do our multiplication, it's equal to 9, not quite greater than or equal to 10, so maybe using the normal distribution would not be the best idea here. Of course, with 0.3, it's way bigger than 10, and it definitely looks normal. 0.5 is normal, 0.7 is normal. But when we get up to 0.9, it's similar to 0.1 in that it's a little bit skewed, and so you wouldn't want to use the normal distribution here, and definitely not here. So what have we seen? If the value of p is close to 0.5, then the binomial distribution is close to the normal distribution, even with a small sample. In this case, we're thinking about situations where the population is divided more or less 50-50, or close to that, 49-51, something like that. In those cases, we can get away with taking quite a small sample. However, if the value of p is not close to 0.5, the sample must be larger in order to use the binomial, or in order to use the normal distribution as an approximation. And if p is really close to 0 or 1, we need our sample to be very large in order to see that normal distribution. One interesting thing is, a normal distribution will eventually appear no matter what. It just takes a really large sample sometimes. So here are the tests that we need to use when we're wanting to use the normal distribution. In order to use the normal distribution, we need two things. The first thing is that the size of our sample needs to be small relative to the size of the population. In this case, we would say that n just needs to be less than 0.05 times capital N, the size of the population, or less than 5% of the population. And then, of course, we have our other rule here. If this follows, then we can use the normal distribution. Basically, this first rule guarantees that the hypergeometric is close to the binomial, that is, we can ignore the correction factor, and the second rule guarantees that the binomial is close to the normal distribution. So when we're dealing with sampling distributions, at least in this class, we're going to typically see these two things. We're either going to see problems that involve the sampling distribution for the sample average or the sampling distribution for the sample proportion. And these are the formulas that we use in each. So let's do one more example. Suppose in a large city, 34% of the population have a pet dog. If a sample of 50 people is taken, what is the probability that more than 20 of that sample are dog owners? So first, let's think about what we know from the information they've given us. First, since 34% of the population have a dog, then we would say that p is equal to 0.34. Of course, subtracting that from 1 would give us that 1 minus p is 0.66, and we're going to be taking a sample of size 50. Now let's see if we can use the normal distribution here. In this case, the first one, that n is less than 0.5 times n, well, notice they didn't even tell us the size of the population, so let's just assume that it's big enough so that we don't have to worry about that. The other thing we can check, if we take 50 times 0.34 times 0.66, we get 11.22, which is greater than 10, and so we should be able to not worry about using the normal distribution. So, when we want to use this normal distribution, we need to think about what parameters we need to use. In this case, the average that we're going to use is 0.34, which is just p, and the standard deviation is 0.06699. So finding the area to the right of 20, if we want to know the probability that more than 20 of the sample are dog owners, then we would say we want to find the probability that x is greater than 20. Now, what we need to do is change this into a proportion, and so we would simply take the number of people we have in question divided by the size of the sample. So what we're really looking for is to find the probability that our sample proportion is bigger than 40%. Of course, using the normal distribution, we can find this area using the z-score, so that z value is going to give us the probability that z is bigger than 0.9. which would be this region. And so therefore, looking that up on the normal distribution table, we get 0.1841. So what this is telling us is that we have about an 18% chance that if we take a sample of 50, there are going to be more than 20 people in that sample, or more than 40% that have a dog. This is the typical type of question that you're going to see dealing with sampling distributions. I hope this video helps to make more sense of sampling distributions and how and when we can use that normal distribution in order to solve them. Thanks for watching.